It's deep in your brain somewhere. All right, 2.1, rate of change in limits. So moving bodies' average speed during time interval is you do the distance covered by elapsed time. Literally, units of measure is length per unit time. So average, you're seeing the difference between them and dividing by how long it took. If you're in physics, this is literally the delta x over delta t. Yeah, maybe? Mm-hmm. Yep. V with the bar, average, delta x over delta t. Your change in position over change of time. Okay, I will erase that so you just don't get confused. You may also recognize this as the slope formula. Average, it doesn't mean every single instant this is exactly how fast you're going. This is the average, right? So when I drive on the 405, there's parts where I can go 80 and there's parts where I have to go 5 miles an hour because people are dumb and don't know how to drive and cut in front of you. Yeah, so, yep.
They're even better in the rain.
Make it very relatable for you. All right. Notice the time interval. Maybe we're not starting at time 1. Maybe I'm interested in, well, what about that time when I was going between LAX and Long Beach, right? So that's not time equals 0 because I left from the valley. So this time interval, I have my initial where I'm starting my interest in, and then the end. So here's the beginning, and then this is the end. All right, so let's go through an example, jog the old neurons. Example 1, an object is dropped from rest. Wait, pause. What does rest mean?
Not moving.
Not moving. If you're not moving, what is your... so if we're dropped from rest, that means we're not moving at the beginning, so that's rad. From the top of the building falls at y equals 16t squared. So this is your position function. Position function during the first t seconds, however many seconds it is. So we want to find the average speed during the first 2 seconds of fall. So what is my t1? What's my starting time? 0. And what's my final? 2. So literally the interval is from 0 to 2, and notice I'm inclusive. I'm including my 2 points, 0 to 2. That's my time. Okay, so looking above at the formula for average speed, I see delta y over delta t. That's just going to be f of, function of my final time, so that's 2, minus the function value at my first time, which is 0, all over my change in time. So final time, 2 minus initial, 0. So keep in mind, this is in feet, and the bottom is in seconds. Just an FYI, right? Because position, it says this many feet. So that's our units of length is feet. And it says seconds for my time. So f of 2, we're going to plug in 2 into the function. So I have 16 times 2 squared minus 16 times 0 squared all over 2. Well, this just turns into 2 squared is 4. 4 times 16 is 64 minus 0 over 2. 64 divided by 2 is 32, and then don't forget your units, feet per second.
Should we do
That's the average.
V with the line?
No, you don't have to. I mean, if this was physics, 100%. But like, I have to be fair, if people aren't taking physics right now, yeah.
I'm not taking physics right now.
Also, source subject.
Okay, so this is not an open invitation to chit chat. Okay, cool. So average 32. At the beginning, it's at rest. It's going 0 feet per second. At the end, it has to be going 64 feet per second. Yep. And so the average is going to be 32. Only at one point would it actually be going that fast. Half the time it's going slower, half the time it's going faster, but this is the average. Okay, so now we can find the speed of the object at 2 seconds and confirm our answer algebraically. So to calculate the average speed over the time interval from the time 2 to any slightly later time, I'm just going to say, okay, t is going to be 2 plus h, where this h is very, very, very small increment. It's just a minuscule amount past 2 seconds. All right? So if I wanted to find the speed at 2 seconds, what I could do is I could make the second time, if I wanted to find it 1 second later, my gap, my h would be 1. So I'd be finding it at 2 plus 1, which is 3 seconds. And as that gap between where I want to find the speed and then the second place, remember how we were finding the slope between the two, and as we get closer, as the gap between the 2 points we're interested in get closer, it approaches the instantaneous speed. The average, which is where you take your start, your end, find the slope between them. As you get closer and closer, it gets to the real value. Okay, so this h, very, very minuscule, so I'm going to plug in my second time. Well, that's just going to be my 2 plus h. Subtract my initial, which is just f of 2, because I'm going from time equals 2 to time equals 2 plus h, my little minuscule, little thousandth of a second later. All over, let's see, my second time, which is 2 plus h, subtract my first time, which is 2. Try to make it more legible. Okay, so now here's where the algebra 2 comes into play. I need to plug this into the function. Remember the function we said was y equals 16 times t squared? Okay, so I have 16 times 2 plus h squared minus f of 2, which is 16 times 2 squared, all over 2 plus h minus 2. Okay, am I okay to scroll over? I think we are. All right, do we remember how to FOIL? Okay, cool. So I have 16 times first 4, outer plus 2h plus 2h, so that's plus 4h plus h squared minus 64 all over h. So 2 plus h times 2 plus h is going to be 4 plus 2h plus 2h plus h squared. So I just did it in one step. I am confident in your foiling abilities now that you have done it for 3 different classes. Algae 1, Algae 2, and Pre-Calc. So, Pre-Calc. Now let's distribute the 16 out. Let's see if anything magically disappears. Distribute the 16. So I have 64, so I'm distributing the 16, so I have 64 plus 64h plus 16h squared minus 64 all over h. Okay, so we see the 64's go away. I have 64h plus 16h squared all over h.
Oh, I kind of remember this now. I mean, it's like
So
the h and then you solve this.
exactly. Well, mostly, yeah. So notice there's an h in both terms on top. Factor that h out. So I have 64 plus 16h all over h. Oh my gosh, h cancels out. I'm left with 64 plus 16h. So, well, that's the limit. We haven't hit the limit yet. I didn't say limit as h approaches 0, not yet. All I'm doing is reintroducing it to you. So depending on how big the little step is, how big h is, that depends on what the speed will be. If I pick it to be 1 second, right, so my h is going to be 1 whole second, I could find the estimated speed if I took it as 1. And as h gets closer and closer to 0, we're getting closer and closer to what number? As h gets closer to 0,
We're getting farther away from
30.
it's closer to 64. Okay, what's your question?
How quickly are you showing the factoring out the age step?
I mean, you could have done it here.
Yeah, that's right.
You could do it here, but no. So either you do it here or you do it here. The point. Sometimes I do extra steps on the homework or on the notes just so like it's clear to everyone where I came from. That was one of my pet peeves in college. I'm like, what? How did you get from there to there? Like, it makes no sense. Sometimes I will leave things to your brain. Like this one, I did not show the full work because I 100% expect you to know how to do this. I expect you to know how to do this one, jog the old memory. We recognize this because it's how we did in pre-calculus, get the cobwebs out, and then like we could cut this step later. Yeah, that's fine. Cool. All right. So I think that's all we had to find for this one, yeah. So remember, H is this minuscule amount. So the smaller gap I make it, the smaller the H is, the closer I get to 64. If I have H be 1 second, I would find it's gonna be 80. If I have it be half, right? If H is 0.5, this would be 72. If I make H be a quarter of a second, 1/4, I'd be at 68. So notice the smaller H gets, the closer and closer I get to 64. And I'm proving it to you right here on the top of the next page. Lead.
Yeah.
So nice. You should like give her a high five or something.
And
What a
he
nice.
stole my pencil. I'm giving him lead for the pencil that he stole from me.
What?
And if you want to play with light, go to the yard.
Come on.
What?
That hurts. Like here.
That's what I was told all of elementary school.
If you want to play with
I'm
lead?
saying the whole 9
Because
yards.
you know, like
Graphite. I'm sorry. Were you getting a sheet of graphite?
yeah.
9 yards.
Okay.
50 cowboys.
So, do we recognize this? Oh, yes. Yes, we do. It's from the bottom of the previous page. Awesome. I'm glad we're paying attention. Okay. So, note, we cannot calculate the speed at the exact instance of 2, because that would mean H is 0. And if I'd plug in 0 for H, 0 over 0 is undefined. So we look at what happens as H approaches 0, as it gets closer and closer. So remember, we have 16, just remember, we have 64 plus 16H. Just remember it was on the previous page. So as my H gets smaller and smaller, notice I'm getting closer and closer to 64. So as H goes to 0, the average speed is a pretty close approximation for what the speed would be at 2 seconds. The average speed is a pretty close approximation to the speed at t equals 2. Because I could plug in 2 for t into my equation, and I find it's 64. But by using this average speed formula, it allows me to like zero in on it. So having this idea of zeroing in on a number, getting really, really close without actually hitting that number, this is like starting to get the idea of a limit, which, surprise, is the next thing we're going to talk about. Okay, so definition of a limit. Assume f, a function, is defined in a neighborhood of C, and let's let C and L be real numbers. Okay, so what the heck does this mean? Let's draw it out just a tad. Okay, so I have what? Did you guys see the topic I uploaded to the Calculus My Jag?
No.
Oh my god.
Can you show us?
Yeah.
Never go online.
So I hit
Yeah, Jake's telling us about the haiku.
go to topics. Oh, what is this right here?
Magic.
Oh my gosh, look at that. Yeah, whatever. I'm gonna talk about Hush, hush, hush. Come on. Shh, 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 shh. Okay. So, what I'm gonna do on the board.
That's so satisfying.
So instead of having, so here, this is what I'm talking about, definition of a limit. And then this is L. So let's look at the definition of limit again. So assume f is defined. So right here, this is my function f, right? This like curvy one, this is my function f. So let's assume f is defined in the neighborhood of C. So this function is defined around C.
Wait, are you screencasting this while writing on the board?
Yes.
You know what? Yeah.
But I don't think I can see what you're referring to.
I'm talking about it. I'm talking about it. Okay.
Happy in class.
Tell me what to do with my life. Okay.
Yeah, are you telling me?
Ah! I didn't mean to click on it. No! Okay. So, if you're at home watching the screencast, cross out A, put C, cross out G, put L. Now you're caught up. Oh my God. Look, this line that, is my function, literally the line these dots are following, that's my function. I'm looking at page 2 where it says definition of a limit. Assume F is defined. So I have this function. Oh my God. I'm just... You guys.
A lot of energy today.
You guys are
It's a
the...
weird day.
Shh. Yeah, we're finishing this lesson today, okay? That's it. Finishing it today. The function f, so this like little curvy line, that's my function f, has a limit L. So here in the GIF, whatever you want to say, that's G. You see G on the y-axis? That's my capital L. That's my limit. What? I don't care. As x approaches, what is this word association? I'm trying to teach you calculus. If you don't learn calculus today, cool, get out. You watch the screencast. Okay. So as x approaches C, or in this moving image, as my x approaches this A that's on the x-axis, as it approaches, given any positive number, there's another number that for all x, we have 0 is less than or equal to absolute value of x minus C, which is less than this little delta amount. And then we have absolute value of the function minus L is going to be, the absolute value is less than this little epsilon amount. So what this means is, as I get closer and closer as I approach it from both sides, I'm squeezing in on a single value. All right, so here I could say the limit of my function as x approaches A, or in our definition as x approaches C, it equals L. Okay, so imagine this moving image, okay? We're going to move back to the notes. I'm going to draw this little picture right here. Oh my gosh, look, here's my function f. Cool. And then I have a, let's see, here's an L. Here's my C. So as I approach C from both sides, all right, guess what? I approach my limit, my L, from both sides. As I move closer, so notice my X, I'm getting closer and closer to my C value. It's really hard to see. Just a moment. No. Because I don't know where the thing is. Okay. Thanks. Sure. All right. So, what I'm trying to show you is as I get closer and closer and closer to C from both sides, I get closer and closer to L on both sides as well. All right. So, if I have a limit as x approaches C, given any positive number epsilon, there's a positive number delta, so that for all of x, the absolute value of how far away I am from my C value, as long as the absolute value is less than delta, then I can say the function minus the limit is also going to be less than the epsilon. Okay, so if you want more information on that, look at your book, come to bonus. The main part I really want you to understand, how do you say this? Oh, the limit as x approaches C equals L. As I squeeze in, as my x values get closer and closer to the one I'm interested in, C, the y value gets closer and closer to the number I want, the limit, which is L. All right, so example, consider the limit sine of x as the limit as x approaches 0 of sine of x over x. So let's consider this by graphing it on your calculator. Look at the y values as x approaches 0 from both sides. And let's see what the actual value is. Oh my gosh. So I'm going to go to the calculator, push the home button, click graph, push enter. Okay. Push tab. Okay, so I want to do sine of x over x. Do we have an idea of what happens?
Yeah.
Sine. Oh my gosh, what the heck is wrong with this? Sine
Why is it glitching out so much?
I don't know. Of course this happens when I'm like trying to show you something. Oh my gosh. I don't think it likes my pen. I think my pen is dying.
Time to get a new one.
Okay, so let me zoom
Oh,
in.
my tutor showed me this one. I didn't know what he was talking about.
Exciting. Let's go ahead and let's zoom in. Zoom in, zoom in, zoom in, zoom in. Okay, do you see how much I zoomed in?
Oh, no.
Oh my gosh, a lot. Okay. Oops, no, I don't want to zoom in anymore. Let's zoom out a little bit. No, it went to the wrong one. I pushed zoom out and it went in.
What is Zoom box?
Okay, so wow, I'm zoomed out. We can see this. Oh my gosh. Oh my gosh. Okay. So, whatever. Look at the y values as x approaches 0 from both sides. What's happening? Do we know?
They're approaching 5.
They approach the same thing.
So as I get closer, oh my gosh.
17,405.
Approaches what? 1. Okay, cool. So we know what we're doing. What? It's going, yeah.
Oh.
So we approach 1 from both sides. Awesome. The limit is 1. It does not matter if f of c exists, right? It doesn't matter if the function exists at that point or if the function is equal to the limit. So let's consider these following examples. So here we see that f of 1, this is a really fat pen. Oh.
Body shaming.
I'm sorry. Do you want to be able to read my handwriting? Cool. F of 1 is undefined, right? So we see literally open circle, undefined. Wonderful. What happens if I take the limit as x approaches 1 of f of x? So literally, I'm looking at the function. As my x gets closer to 1 from both sides, so I'm approaching it from both sides. What is the value I'm approaching? 2. I'm approaching a value, a y value of 2. As x gets closer to 1, I see I get closer to a value of y value of 2. Awesome. So this is an example of this function. So notice that this is a removable discontinuity. And the reason it's removable is because if I factor out x squared minus 1, that's literally x plus 1, x minus 1, check it out. X minus 1 cancels out. And this is going to be the graph of x plus 1, except x cannot equal 1. Remember how we did this one? X plus 1, but x cannot equal 1. Removable discontinuity. Wunderbar. Wonderful. Okay. So, let's look at the next one. G of x. Huh. It actually is defined. Look at this. F of 1 is equal to 1. Weird. Weird. I'm sorry, this is g of 1. But if I take the limit as x approaches 1 of g of x, it's equal to 2. As I get closer and closer to 1, as for x equals 1, my y gets closer and closer to 2. Alright, as I get closer, as my x approaches x, as we choose x values that are closer to 1, my y values get closer to 2. But the value of the function at 1 is not 2. So this is a piecewise function. It's the function we just had, except I now have a value at x equals 1. Here, interesting. Let's see. If I say h of 1, I see it's actually 2. I have a value of 2. And if I take the limit as x approaches 2 of h of x, well, as I get closer to 1 from both sides, as I get closer to x value of 1, I get closer to a y value of 2. So I want you to notice these three graphs, what? I'm sorry. X approaches 1, y approaches 2, thanks. You're just playing with your calculator? Whatever, okay. whatever. What I want you to notice is all three of these graphs have the same limit. It doesn't matter if the function value exists there or if the function value is equal to the limit, we still could have a limit. So what you can do is you could like cover up the hole. If you're approaching the same number from both sides, you have a limit. Awesome. Doesn't matter what if it doesn't have a value, the function doesn't have a value, or if the function value is something else, I could still be approaching the same number from both sides. That's the point here that I'm trying to make with these three graphs. Properties of limits. So you may recognize these examples from the quick poll. Hey, okay. So limit as x approaches a number of a constant. Literally, limit of 3 as x approaches 2. So do you know what this looks like? If I say limit of 3 as x approaches 2, well, let's graph it. This is literally y equals 3. That's going to look like a graph like that. 1, 2, 3. So that's 3. So when x equals 2, what's the y value? 3. So that's what it means is, guess what? If you're taking limit of a constant, it's just going to be that constant. Okay. And then limit of x as x approaches c is equal to c. Okay, what the heck does this mean? Well, if I'm taking the limit of x as x approaches 3, this is the same thing as if I, let's see, graphed y equals x, right? Because I've set this equal to the function value. So I have y equals x. So when my x value is 1, 2, 3, my y value is also 3. It's the identity function. So limit of x as x approaches any number is whatever number you're approaching, because this is just the identity function. Do we have questions so far? Do we remember this? So if I gave you the quick poll now, we'd get hundreds?
Yeah.
Maybe?
Yeah.
Okay, what if I took limit of 45 as x approaches 2? What is the answer?
45.
45. Awesome. Sorry, I should have wrote it up here. As x approaches 2. What about the limit of x as x approaches 60? 60. Okay. So this is two other examples for both of these properties. So this is limit of a constant, limit of the identity function. So other properties of limits. If you have two different limits, so I'm taking, and you're approaching the same x value, you can add the limits together, you can subtract them, multiply them, and if you're taking the limit of a constant times a function, it's literally just going to be the limit of the function times the constant. What's wrong?
Are you multiplying? Are you?
Really?
Town hall, baby.
Terrified. I don't like speaking in front of public.
You got this.
Wait, what?
We're all in reading.
His drashad is tomorrow. Okay, so you guys can like look over this. This is mostly a review. Let's go on and do the example, because I feel like if we actually use real numbers, you'll understand it better. So example 2, use the fact that limit of k as x approaches c is k, and limit of x as x approaches c is c, and the properties of the limits to find the following limit. Okay, what is the limit of pi as x approaches root 2?
Pi.
Pi. This is the limit of a constant.
Oh, because pi's a constant.
Yep, limit
Yes.
of function with constant value. So I'm writing this because guess what? You can look above in your notes and be like, oh yeah, pi is a constant. Got it. All right, B. Let's check it. So limit as x approaches a of 2x squared minus 5x plus 3.
A.
So you're just plugging this in for x. So it's going to be 2a squared
5a plus 3.
minus 5a plus 3. Cool. Because this is the limit of the identity function at c. So literally if you're just putting in the limit of a function and you're like, oh, what's the limit as I approach a certain number? You can like put it in, see if you get a value or not. Polynomials and rational functions. So if we have a polynomial function, if you draw a polynomial function, there's no holes. It's continuous. It's smooth. It may have like some curvy curves, whatever, but it's literally, it's gonna like go on forever in both directions, right? Whether going to infinity or whatever. Polynomials, remember, x squared, x cubed, x to the fourth, they don't have holes. That's all we set up. They don't have holes. So here, all of this stuff in this first number 1, all it's saying is, hey, if you want to take the limit of a polynomial, just plug in whatever x value you're wanting and it will tell you the limit. Because there's no holes, whatever the function value there, it will also be your limit. Cool. So notice if you graphed x squared plus 3x minus 4, you'll just get a nice function. There's no discontinuities. I'm getting sick. So just plug it in. So I have 2 squared plus 3 times 2 minus 4. 4 plus 6 minus 4 is 6. All this is saying is, hey, you want to take the limit of a polynomial? Cool. The limit will be the same thing as the function value. Find the function value. Done. All right. If f of x and g of x are polynomials, we have a rational function now. This is an issue. This is an issue. Because potentially, guess what? It could be divided by 0. So as long as I'm not dividing by 0, I can just plug it in. So as long as c is not 0, as long as I'm not approaching 0, this will be fine. As long as the bottom doesn't go to 0. So I can plug in. So I have negative 2 plus 1 over negative 2 squared. Negative 2 plus 1 over 4 is just going to be negative 2/4, which is negative 1/2. Wait, did I do this wrong? Yep. Yes, plus 1 is negative 1/4. Yeah.
What happens if that's x?
Well, you can't divide by 0. That'll be an asymptote, so it won't have a limit. It'll be have a discontinuity. Remember vertical asymptote? Yeah. So I will be approaching like infinity or negative infinity, and that's not actually a number. Yeah. All right, determine the limit by substitution. Support graphically. I'm going to give you guys like 15 seconds. Try out A and B. And then when you're done working them out algebraically, put them in your calculator to double check they're correct. So try out A and B of number 3. Did you do it already? Yeah?
Wait, just substitute.
Yeah.
Yeah.
Okay, so as Noah said, it's just substitution. You just substitute in for x. Because if it's a polynomial function, we're good. Literally, the function value will be the limit there. So I have 2 cubed minus 2 times 2. 8 minus 4 is 4. So as long as I'm not approaching a number that will make my function equal 0, I'll be okay. And I see that putting in 1 down here puts a number on the bottom, right? I won't be dividing by 0, so I can just plug in to find the answer. So plug in a value of 1, such as 2 minus 7 plus 4 plus 5 over 3 plus 1.
1.
So
7
5, 4 over 4 is 1. Awesome. Determine the limit graphically. Confirm algebraically. Okay. So let's go ahead and this first one, ooh, trouble is brewing. So first let's see if anything will cancel out. How do I factor?
The bottom.
Yeah, it makes it
It's
0.
unacceptable.
Yeah, so I see I'm approaching 0 if I plug it in. So I need to, if I can factor and cancel anything out. T minus 2, t plus 2, and what at the top? What adds to negative 3 multiplies to positive 2?
T minus 2, T minus 1.
T minus 2 and t minus 1. Okay, so I see that this cancels out. I will have a removable discontinuity at 2, but let's see if we actually have a limit there. So we evaluate the limit as t approaches 2 of t minus 1 over t plus 2. So this is going to be 2 minus 1 over 2 plus 2. So it would be 1/4. Okay, so what this is telling me is, guess what? This graph, it's going to have a hole at t equals 2. It'll be some kind of removable discontinuity. So it probably does something like, I don't know, maybe something like this or whatever. But the fact is, right here, if I zoom in, there's a little discontinuity. I'm approaching the same number from both sides. I have a limit, but I don't actually have a function value. All right, ready to try the next one?
Yeah.
Cool. So this one's trouble, because right away, if I plug in 0, I'm dividing by 0. That's not good. Let's see if we can simplify this at all. So first, I'd like to simplify the top, the numerator. I see I'm, subtracting 2 fractions. So I need to make sure I'm have a common denominator. So I multiply this left one by 2 over 2. Multiply the right one by 2 plus x over 2 plus x. I will now have a common denominator of 2 times 2 plus x. So this is going to be 2 over 2 times 2 plus x minus 2 plus x over 2 times 2 plus x all over x. So, how'd I get 2? Yeah.
You can't just multiply by 1/2.
What?
You can't just multiply by 1/2 to get the denominator.
Multiply by...
2 over 2. Can you do 1 over 2?
No, because then it changes the problem. So anything multiplied by 1 is itself. It doesn't change the problem. So if I multiply by 2 over 2, the same thing as multiplying by 1. Yeah. Otherwise, if I multiply by half, it changes it. Okay. So now that I have this, I can, condense a little bit. So 2 minus 2 plus x. Okay, this is literally just going to be x over 2 times 2 plus x all over x. I did not leave myself room to write limit what?
I'm just asking it for a limit.
Yeah. Just trying to make it clear, the division signs. Okay, so, oh wait, this is a minus x. Yeah, it's a minus x. Because I distribute that negative out right there, it's that negative. Okay, so he says flip it and multiply. So if I take the limit as x approaches 0 of, let's see, negative x over 2 times 2 plus x. Instead of dividing by x, I can multiply by the reciprocal, which is 1 over x. So instead of dividing by x, same thing as instead of dividing by x, multiply by the reciprocal. So I see that this turns into limit as x approaches 0 of negative 1 over, can we just, yeah. So 2 times 2 plus x. So if I plug in 0 here, I have negative 1/4. I don't know why. It's like the third problem on this page. It was 1/4. Okay, let me take a second here. Are we okay? Was this pushing a little too fast? I think we're okay. It's just like cobwebs. That's why there's a whole day to review this. One-sided and two-sided limits. So what I've been talking about so far was, well, I have a limit if I'm approaching the same number from both sides. So what I can do is say, okay, what am I approaching from the left side? Then, what am I approaching from the right side? Then I say, are they the same thing? If they're the same thing, limit exists. So one-sided limit says, hey, as I come from the left side, what am I getting closer to? As I approach from the right side, what am I getting closer to? And then if the two are the same number, the limit will exist. Otherwise, it won't exist if I'm approaching two different numbers. All right, so right hand, if I'm approaching from the positive, right? This little plus up here means from the right side. If you think of a number line, negative, positive. So if I'm approaching from the positive side, I'm coming from the right side. If I'm coming from the negative side, right here, I'm coming from the left. So wherever you're coming from, the positive side, oh, you're coming from the right. If you're coming from the negative side, oh, it's coming from the left. All right, that's what this is saying right there. A function f of x has a limit as x approaches c if and only if the right hand and left hand are equal and they both exist. So as long as I'm approaching a number from the right hand, approaching a number from the left hand, and they're the same number, I'll have a limit. Cool. All right, so let's try this graph out. I'm just going to call some random people. I just want it to be the right size so we can... Perfect, this is good. How about we go with Noah, let's do A. Which side am I coming from, left or right? Left side. How can you tell? Comes from the negative. So if I come from the left side towards 0, I'm approaching 5. Ariel, what about from the right side?
Negative. Oh no, wait. Yeah.
So as I approach 0 from the right side, from the positive side, I'm also approaching 5.
Oh.
Were you on a different problem? Maybe.
No, I was thinking.
No worries. Okay, so I have the left side, I have the right side. Guess what? These are the same numbers. So now I come down here and I say, okay, well, what's the limit as x approaches 0? 5. As long as they're the same number, it will exist. Wonderful. Let's go, Maya Hamaides. What about D?
Is it 2?
Let's see. So this guy is approaching from the left side. As we approach -3 from the left. As we approach from the left, what am I approaching? 0.
How come it's not like, when is it like doesn't, it's just for...
So I'm looking at the left side limit, left hand limit. As you approach from the left, what number am I getting to?
Like f would be the not...
What?
It only does not exist when it doesn't like match.
If they don't match, then it will not exist. Or if I'm going towards infinity, it will not exist. Or if I'm approaching different numbers from both sides, it won't exist. Okay, what about Hannah Fahuna? What about as I approach from the right side?
5.
Alright, as I approach from the right side, I'm approaching 5. And guess what? These do not match. So, since they don't match, that does not exist. The limit does not exist. As Lindsay Lohan would say.
Isn't there some rule about
What would she say?
the hoo-ha,
What would she
fill
say
in circle?
Well, this is the function value. This is f of -3. So
it's not the limit value.
So it's the right. This is the function value. So what you're thinking of is continuity. A function is continuous at a point if the left-hand limit and the right-hand limit are the same, and that limit equals the function value. So that's like the next thing we'll talk about, but not yet. Right now we're just focusing on limit.
The homework isn't done.
What?
What would Lindsay
Or,
Lohan do?
do we, what? We still got. Can we?
Wait, why would she say that?
2 minutes. It's her next
Okay, I guess this is a good place to stop. This will take like 5 minutes next class. We'll do this.